Think you know how planes fly? Re-examine the mechanics of aerodynamic lift. While classic lessons rely strictly on Bernoulli's principle, highlighting high velocity, low-pressure air flowing over the top of the wing, that's only part of the equation. True lift demands Newton's laws of momentum conservation, where lower velocity and higher pressure underneath propel the wing upward. By balancing topside pressure drops with bottom-side momentum transfer, this slide challenges traditional textbook explanations to reveal how airplane wings actually generate lift. Forget the common textbook myth claiming that air parcels split at the front of a wing must magically reunite at the trailing edge. Known as the equal transit time fallacy, this flawed concept incorrectly assumes that air flowing over the longer upper path is somehow glued to the air moving underneath. In reality, physics imposes no such reunion rule. The air streaming over the top actually arrives far ahead of the lower flow, disproving a century of lazy explanations about how aerodynamic lift really works. Wind tunnel data reveals the true physics of flight. Air flowing over the top of a wing does not merely keep up with the air underneath, it utterly outpaces it. As the diagram illustrates, the upper airstream accelerates so rapidly across the curved surface that it reaches the trailing edge well before the air underneath even reaches halfway. This dramatic speed difference drastically lowers the pressure above the wing, generating the required lift. Far from reuniting equally at the end, the top air is literally racing ahead. To understand flight, physics turns to two scientific titans, Daniel Bernoulli, who framed fluid dynamics through pressure and energy, and Isaac Newton, who described force through momentum. While debate persists over which perspective better explains aerodynamic lift, both provide complementary frameworks for the same physical reality. Remarkably, neither giant ever actually attempted to explain airplane wings. Their fundamental principles were only applied long after their time to unlock the secrets of flight. Daniel Bernoulli's principle dictates that fluid velocity and static pressure are inversely related, driven by the conservation of energy. As fluid flows through a constricted Venturi tube, it accelerates through the narrow center, causing internal pressure to drop to its lowest point. Once the channel expands, the fluid slows down and pressure recovers. Encoded by the equation, the pressure equals 1/2 the density times the velocity squared, which equals a constant. This fundamental rule proves that whenever a fluid speeds up, its pressure drops, providing the key mechanism behind pressure differentials in aerodynamic flow. Applying Bernoulli's principle to an airfoil demonstrates how accelerating air creates a low-pressure zone above the wing, producing lift. Bernoulli's formula accurately calculates this pressure drop based on the increased flow velocity. However, this classic model reveals a fundamental limitation. While it precisely describes the relationship between airspeed and pressure reduction, it completely fails to explain why the air accelerates over the top of the wing in the first place. Beyond pressure drops, aerodynamic lift relies on direct physical deflection, the skipping stone effect. Because air possesses mass, an inclined wing moving through the atmosphere physically shoves thousands of pounds of gas downward. By forcing this massive volume of air out of its path, the wing triggers Newton's third law: for every action, there is an equal and opposite reaction. Pushing air downward creates a powerful upward reaction force, proving that flight is as much about physically deflecting mass as it is about fluid pressures. Newton's third law grounds flight in the conservation of momentum. As an airfoil moves forward, it accelerates a continuous mass of air downward, creating an action known as downwash. Governed by F equals ma, this downward acceleration of mass generates an equal and opposite upward reaction, lift. While fluid pressure offers one perspective, Newton's force equation proves that staying aloft relies on a physical exchange. The wing continuously shoves air down so the surrounding air pushes the aircraft up. Fluid dynamics reaches its conclusion through flow deflection and the Coanda effect. As air moves over the wing, fluid viscosity causes the airstream to cling to the curved top surface, physically turning the entire flow of gas downward. By actively directing this stream toward the ground, the wing creates a massive downward push. In response, equal and opposite forces propel the airplane upward. Ultimately, lift is teamwork between pressure and momentum. The wing shapes the flow, pushes the air down, and the deflected air pushes the aircraft into the sky. Aerodynamic lift is not a debate between Bernoulli and Newton, both principles are correct and required. Flight demands the simultaneous conservation of energy and momentum. Bernoulli's principle accounts for the low-pressure zone created by accelerating air above the wing, while Newton's laws explain the equal and opposite upward force generated by downward air deflection, or downwash. Neither model alone provides the full picture. True aerodynamic lift exists at the intersection of both, where pressure differentials and momentum conservation work together to hold an aircraft aloft. Understanding aerodynamic lift requires separating myth from physical law. The equal transit time theory, which falsely claims upper air speeds up simply to catch lower air, is entirely false. Instead, genuine flight relies on two valid, complementary perspectives: Bernoulli's pressure lens, which calculates force via energy conservation and pressure drops, and Newton's deflection lens, which explains downwash using momentum conservation. Together, both true principles provide the complete blueprint of lift. Moving beyond simplified models, aerodynamics relies on the Euler equations. Derived in 1752 by Leonhard Euler, Daniel Bernoulli's student, these fundamental formulas unify fluid dynamics into a single mathematical framework. Rather than treating pressure and deflection in isolation, the Euler equations simultaneously conserve mass, momentum, and energy across a moving fluid. By accounting for all three physical laws around an airfoil, Euler's formulation seamlessly connects Bernoulli's pressure differentials with Newton's downwash, capturing the complete, exact physics of aerodynamic lift. Real-world flight embraces true complexity through the Navier-Stokes equations. Going beyond idealized models, these equations account for air viscosity, surface friction, and chaotic turbulence surrounding an airfoil. Capturing these intricate, swirling vortices represents one of the deepest challenges in fluid dynamics, so profound that proving the existence and smoothness of its mathematical solutions remains an unsolved Millennium Prize problem. Beyond basic pressure and momentum, aerodynamics lives in the beautiful, unsolved boundary of mathematical physics. Look up. The next time you see an aircraft soaring overhead, remember that its flight isn't magic, it's a masterclass in physics. From Bernoulli's pressure differentials and Newton's downwash to Euler's unified equations and the turbulent beauty of Navier-Stokes, simple air molecules make human flight possible. Science isn't trapped in textbooks or formulas, it is active all around us. Look up, appreciate the forces carrying millions across the sky, and understand the incredible physics of our world.